Hello. Today we're looking at section 2.6, which is on planes. So equations of planes in 3 space. Okay, so let's think about how we could define a plane. Well, kind of like a line, we need a point and a direction. However, if we think about a direction in a plane, right, if you think about a pen line on top of a piece of paper, that piece of paper can actually rotate around that pen. Right, that doesn't make that a unique direction for that plane. So it's a little bit more complicated than we had with a line, and I guess that makes sense. And so what we do is we do this. We imagine a sheet of paper or cardboard. I guess cardboard makes more sense because it's solid. And that's our plane. And then we imagine a little nail that's sort of perpendicular, just sticking into that piece of cardboard. The direction of that nail, as long as it's perpendicular, uniquely determines the direction of that piece of cardboard, right? And then the point in space determines where it is. So here's a diagram of kind of how that would look, right? So our P is our point. Our nail there is perpendicular, and we call that the normal. It's the normal vector to the plane. And that uniquely determines the direction of the plane. I'll say with the point, that means we just have one plane that could satisfy that. And so we have our definition or equation for a plane. Okay, but well, how do we go about doing that? Okay, so first off, what we do is we can take 2 points that are in the plane. Okay, we'll call them P and Q. And so the vector PQ is between those 2 points. And in particular, the normal vector n is perpendicular to PQ for any PQ. Right, we could take any 2 points in the plane, and that normal vector will always be perpendicular to that vector. So the normal vector is normal to every vector in the plane. And so in particular, how we write that mathematically is that the dot product of n and pq is 0 for any p and q. Right, so remember when we talked about dot product, if the dot product was 0, they were perpendicular. Orthogonal was another word we used. Okay, so given that fact, let's go ahead and try and create this formula. Okay, so we're going to let P be a point in the plane, and we're going to kind of fix P. So I'll call P x0, y0, z0. And so that's a fixed point in the plane. N is the normal vector to the plane, right? So that's the thing that's orthogonal to everything. But Q now is going to be any other point, and the any there is important. It's any other point in the plane. Okay, it could be near P, it could be far away from P, wherever it goes. And if we do that, then PQ is given by this, right? X minus x0, y minus y0, z minus z0. But I say x, y, z now at all or any of the points in the plane, whereas x0, y0, z0 are fixed. And so now we take the dot product between PQ and n and set that equal to 0. Also, it's the dot product of these two vectors, which of course is pretty straightforward to calculate. We just multiply each element piecewise and add them together. So we get A times x minus x0, B times y minus y0, C times z minus z0. And all that has to equal 0. But if we now distribute the A and the B and the C and take all the bx0, by0, c z0 over to the right hand side, we get this. But notice on the right hand side here, right, the ax0, by0, c z0, that should be a z. These are all just constants. Okay, and so you just add a bunch of constants together, you just get another constant. So sure enough, we can write this in this form where it's ax plus by plus cz equals d. And notice the coefficients of the x, y, z there are exactly the elements of n. Okay, from that all we have to calculate is the d, and that's based on the point we choose. Okay, and so just putting this all together in a definition. So the equation of a plane in standard and general form. So the standard form is that a x minus x0, b y minus y0, c z minus z0 equals 0. The more general form is ax plus by plus cz equals d. Okay, those are our definitions for the equation of a plane. Okay, so let's go ahead and do that. So let's think about 3 points that are in our plane, right? So if you imagine a plane, you have 3 points, you've uniquely defined a plane. So from those 3 points, can we get the equation of the plane in standard form? Okay, so based on what we did previously, the very first thing we need to do is get that normal vector, right? That vector that is perpendicular to the plane. And to do that, well, how do we find a vector perpendicular? Well, if we have two vectors, to find a vector perpendicular to each of those, we take the cross product. So there's more than one way of doing this, but if we kind of fix that point P and then go from P to Q and P to R, that gives us two vectors in the plane, and we can find the cross product of that to find something orthogonal. So I say we go from P to Q and P to R, and I say that's not unique. We could have chosen Q to P and Q to R, or some variation on that, but this seems the simplest. So PQ, well, so how do we find PQ? Well, we take the elements of Q minus the elements of P. How do we find PR? Well, the same way. So we take the 0 minus the 1 minus the 1, and the 2 minus the 0. And so that gives us the two vectors, PQ and PR, and now we can take the cross product of those two vectors, and we get 2, 1, 1, and that is our normal vector. Right, that is the vector that's normal, that's orthogonal, that's perpendicular to our plane. Okay, and then once we've got that, actually the last piece is really easy. All we need is a point in the plane. Well, we have 3 points in the plane. We could have used every single one. I used P. So we take 2 times by x minus 1, right? The 1 coming from right here in the P. And then 1 times by y minus 1. And then 1 times by x minus 0. I'll say we could have used Q, we could have used R, we just chose to use P sort of arbitrarily. And that is indeed the equation of the plane. And that's about it, right? So this is the plane that contains these 3 points. And you can always check that, but indeed it does. Here it is diagrammatically, and of course, as always, it's a little hard to see 3D shape on a 2D picture, but I think you kind of get the idea. So here's our plane, and you can see the points P, R, and Q that are on the plane. Not only that, you can see labeled in the kind of the blue, we have the vectors PR and the vector PQ. And then you can see jutting out to the left there, that is the normal vector, right? That is the cross product of PQ and PR sticking out perpendicular to our plane, because that's how it works with the cross product. And that's actually it, right? Once we've got that vector, that cross product vector in that point P, that tells us everything we need to know about that plane, that uniquely defines that plane. And there is the equation. Okay, so let's take another example. So suppose we start with lines this time rather than points. So we have two lines, L1 and L2. First off, we want to show that they intersect. If they don't intersect, I don't know how we'd form a plane of them. We can move them around, but if they don't intersect, I don't think that works. So let's show that they intersect and find the plane that contains both of those lines. So there's a plane defined by those. Well, they're not parallel. You can see that straight away, right? 2, 1, 2, and 3, negative 2, 1 are the two directions. And one of those would be a multiple of the other if they were parallel, which is not. So if they're going to intersect, well, they have to intersect to the y position, the x position, and the z position. And so we get that. And so just kind of solving that, I won't go through the details, but solving that, we get s equals 2, t equals negative 1, and that works for all 3 of them, right? It doesn't just work for 2, it works for all 3 of them. So those 2 lines intersect. Again, because they intersect, we can create a plane from them. Okay, so again, let's just go back to these lines. We know they intersect. Let's create a plane. So 2 vectors on the plane, well, that's again pretty straightforward. We can just take the directions of L1 and L2. So the direction of L1 is 2, 1, 2. The direction of L2 is 3, negative 2, 1. And so we have 2 vectors, and we're kind of at the point we were at previously, on the previous example, where we had 3 points now. We have 2 vectors. We can find the cross product of those 2 vectors that are in the plane, and that'll give us the normal vector. So we take the cross product of 2, 1, 2 and 3, negative 2, 1, which will give us 5, 4, negative 7. And that 5, 4, negative 7 is the normal vector, right? That's perpendicular to what we have, the normal vector. And now we can pick any point on the plane. And again, there's infinitely many of them, but there's 2 easy choices. If I take the line L1 and just set s equals to 0, if I set s equal to 0, then I get a point on the plane. I could have set s equal to 1 or negative 1 or 50 or whatever I wanted. I could have also taken a point on L2, done a similar thing, but any way we do it, it will work. And so if I take that point, negative 5, 1, negative 4, plug it into our equation, right? So we have the 5, 4, negative 7 of the coefficients. Then we have x minus minus 5, y minus 1, and z minus minus 4 to give us these two values. And so we plug it all in. And then we just solve it to get the general form. So distribute the 5, distribute the 4, distribute the negative 7. And we get the 25, negative 4, negative 28, and take that over to the other side. So the equation of our plane is 5x plus 4y minus 7 equals 7. Okay, so again, just recapping that. So we had two lines. We used their directions. We took the cross product to find the normal vector. We picked any old point on the plane, which meant any old point on the line, and then created this kind of general form of the equation. And that is about it. Thank you.